In this video, we are discussing a technique called paper chromatography. This is a separation technique that we use to separate a sample of mixtures. In today's video, I'm going to be focusing on how this technique is used to separate a mixture of colors. I'm going to be analyzing a sample of sweets. I'm going to be going through the practical techniques, some of the common errors that you might make, and finally, I'm going to be going through RF calculations towards the end of this video. We're going to set up our paper chromatogram, and it's really important that we use a ruler and a pencil for this bit. And what I'm going to do now is I'm going to draw a horizontal line in pencil that's roughly 1 centimeter above from the bottom, and like that. And the idea is I'm going to put my samples that I'm testing along these lines. So I'm going to start labeling it. So I've got the first food additive, which is E133, and then I've also got E100, and I've also got E132, and I'm also going to leave a bit of space for my test sample, which is obviously the Skittles. So now what we have to do is to obviously get our samples. So I've got to start off with the first one, E133. I've got a capillary tube, and this capillary tube allows me to draw up a small sample of this substance and allow it to spot it on that paper. So I'm just going to do that quickly. Okay, so here we go. It's the first one, E133. Just a tiny dab. That's enough. Then the next one that I've got is E100. We'll do about the same. Just going to put a sample of E100 in here. Has a bit more force. There you go. And then the last one that I'm testing is E132. That's about more than enough. I'm going to put a sample of that on there. That's about enough. Okay, now obviously the only remaining sample is my Skittles. Now obviously the Skittles, as you can see, they're in solid form, and what I'm going to do is I'm going to dissolve some water in them, and that will cause the color to dissolve into the water. So after adding some water to the Skittles, you can see the colors that were on the Skittles have dissolved into the water, and I'm now going to get a capillary tube and I'm going to put a sample of that onto the actual paper. So here we go. Okay, and that is it. Now for the final part of this experiment, you will need a small beaker and also some water. So the water will act as our solvent, and what I'm going to do, I'm going to add just a little bit of water. It's really important to not add too much water. When I put this paper into the beaker, the solvent should always be below the start line. So that's that pencil line, that horizontal pencil line. The solvent should never go above that line. If that happens, your samples will wash away into the solvent and they will dissolve and disappear before they've even had a chance to separate. So just add a little bit of more water, too much. And I'm going to then place my paper, and what I'm going to do is I'm going to let the water travel up, as you can see, and then what will happen is my sample will separate. So after about 6 minutes, I've taken the paper out, I've let it dry. You will notice that there is a horizontal line at the very top in pencil. That line here just simply represents the distance of the solvent. This will be important later on when we calculate something called the RF value. But first we're going to analyze these results and make some sort of conclusion about what the Skittles sample contains. So we're going to first match the heights. If you see Skittles sample here, it's got two substances, one here at the top and one down here. And so we're going to use the ruler to help us match the heights. And from what I can see, the first spot at the very top, doesn't match up with any of the 3 additives, so we can say it doesn't contain that. If we go to the last one, we can also see it doesn't match up with any of the heights in those 3 food additives. So we can safely conclude that this Skittle sample contains 2 food colours, but neither of these are E132, E133 or E100. So for the next part of this video, we're going to be doing a calculation for this value here called RF. Now this stands for retardation factor. Some of you may know it as retention factor, and it's calculated using this equation here, which is the distance of the spot divided by the distance of the solvent. So we're going to use our results as an example. So there's our paper. I'm just going to zoom into that a little bit so you can see it. Okay, so the first thing I'm going to do is I'm going to measure the distance of one of these spots. So I'm going to choose the distance of the spot E132, which is over there. So I'm going to get my ruler. I'm going to measure it from the start line to about the center of that spot. A bit difficult sometimes. There you go. And that measures about 6.1. So I'm going to write this down. So we've got 6.1. Then we're going to measure the distance of the solvent. So we're going to start again from our start line over here, all the way up to the line at the very top over here. And that measures exactly 7 centimeters. And so we're just going to divide these values. So we're going to do 6.1 divided by 7, and the answer we get for that, let's have a look at the calculator. So we get this value, 0.87, so to 2 significant figures, we're going to say the RF value is 0.87. Now this value can never be more than a 1, because your solvent here will always be higher than your spot. If you get a number higher than 1, what that indicates is that your spot has traveled further than the solvent, say up to here, and obviously that's impossible. So whenever you divide these, make sure your answer is always less than 1. Now, a couple more things. The higher this value, or the closer it is to 1, the more soluble that substance. Okay, and obviously if your sample doesn't go anywhere, say it's still at the start line, then the RF is 0, and so we can say that the solubility of that compound in that solvent is insoluble.